starting derivatives today. You'll need to bring your book from here on out. Now, I told you last week, I'll tell you before you need your book the day before. I'm not that organized. I way over some accountability. That said, you will want to take it home with you, but if you don't have it with you right now in class, you're fine. We're going to be working from this room. All right? Okay, here we go. So as a starting point, I know it says the intermediate value term. So as a starting point, will you get yesterday's homework out and look at the last problem, please? This is meant to be a set the stage for today. So the Usable / restriction running table problem. See where I'm at? Okay, we'll get through a lot more, and we'll have a way better time if you all take it. Or nope. Yeah. All right. So here we go. This is not. I didn't actually analyze the video, nor did I actually run because it's ridiculous. But this is just a made-up table of stuff, and Usain Bolt actually runs the 100 in less than 10. But you get the idea. The point is still made. So here's the deal. I tell you at different times where Usain Bolt is on the track. And I could graph that data, but the main goal is to say, how fast is he running at time equal 3? Now, this how fast speed is change in position over change in time. Way back from physics, right? Oh, some of you are juniors. Did you learn that yet in physics? Okay, well, take my word for it. It's change in position over time. So change in position over time, how, like miles per hour, right? Velocity would be directed position, change in position over time, but we don't need to go there yet. So the problem is that this is average speed between 2 points. So I could, for example, take his total change in distance over the whole time frame, 100 meters over 10 seconds, and get his average rate, 10 meters per second. Yeah? But does he go at a constant rate the whole race? Does he start instantly at 10 meters per second? No. All right. Now, that problem just right there caused mankind trouble for 5,000 years. How do I find how fast he's going at one instant? Not over a time interval, but at 1 second or one split second. How fast is he going? And the theory was for 5,000 years, well, you can't find change between a point in itself, because if you are a point and there's no change, you're staying there and it all breaks down. But with the idea of a limit, well, what if I, instead of taking 1 point, I just take 2 points as close as I possibly can to each other? Well, then you start to get close to that, what is it, right at 3, all right? Now, in an ideal world, I could take a really quick snapshot and say, at 3 seconds he's here, and at 3.00001 seconds he's here, and get a tiny little interval. Now, if I had an equation, I could actually do that because I could get whatever points I wanted. But with a table, you're kind of limited. The idea, though, is if I want to know how fast he's going at 3, I don't want to look at the whole interval. I want to get as close a window as I can around 3. So what did you use? 2 and 4, all right? This is a bad estimate. Instead, better is to use 3 or 2 and 4 because it's a smaller window around 3. So between 2 and 4, how far did he go? What was his position change? 25 meters. And how long did it take? 2 seconds. And so a better average is 12.5 meters per second at time equal 3. And this is probably closer to his true speed at 3, time equal 3. Now it's still, though, an average speed. It's an average speed between time 2 and time 4. It's not the speed at the instant. So the play today is between instantaneous rate of change and average rate of change, and that's what the heart of the derivative is. So what's the tightest possible window you could get for mean? You wouldn't use 0 to 34 seconds, which is how long it took me to run 100 meters. Apparently I had a real trouble there between 4 and 3. I just got tired. So what window would you use to get as close as possible around 3? 3 and 4. We have to use 2 points, right? And I need change in position. So what's the change in position if I take these two? 10 meters over how long? How long did it take me to change that position? 1 second. So an estimate of my speed at time 3 would be about 10 meters per second. It's probably a little optimistic, but you know. All right. Now let's talk about those notes here. Here we go. The very definition of the derivative. Now, let me first emphasize this, especially those of you who have seen calculus. There are 2 levels to the derivative. Taking the derivative and knowing what it means. And it's tempting to boil down a derivative to just shortcuts. For example, I could teach a 5-year-old to calculate the derivative. I would just tell them it's really 2 steps. You bring that exponent down, and the new exponent, that new little number I would call it, he wouldn't know what an exponent is, but you now reduce it by 1 less, and that's the derivative. And that would mean absolutely nothing. You found the derivative, but it means nothing. Now, my point then is this. Please don't boil derivatives down to just some silly shortcuts. That is not what a derivative is. Actually understanding what a derivative is in your soul comes from this idea. All right? So let's go here. At its heart, the derivative is trying to find change at an instant instead of change over a time interval. Let's start here. The goal of a derivative is to find the rate at which function is changing at one instant in time. As I said, graphically, this is called a tangent line. Tangent line is a line that touches at one point. What is it? It touches the curve at one point, I guess I should say. All right? Now, we'll come to that in a second. Theoretically, it's impossible to find slope between a point or change between a point. If I said, hey, here's 1 point, draw the slope through it. Is there one slope through 1 point, or is there many? Okay, there are many. But the minute I put 2 points down, is that one slope? Oh yeah, there's only one way to draw a slope. Now, you can start to approach slope at a point if I take the 2 points closer and closer and closer together. Well, then I can start to get slope at a point. That's the idea of the derivative. Here we go. Did I have this as labeled as point? Is A at the 1 tick mark or 2 tick marks? Where is that? Okay, so A is 1 tick mark. If I wanted the tangent slope or the instantaneous rate of change, it would look kind of like this. That's a tangent. And I am going to do, that's all calculus. A lot of balancing or mixing between graphical and analytical and even numerical. All right? That's my goal. That's the instantaneous rate of change. How do we find it? We'll figure that out in a second. All right? Let's start by saying, what if I took, we just said I can't find the slope between 1 point and itself, so instead I'm going to make up a second. I want you to draw what's called a secant line. A secant line is through 2 points in the graph. So a tangent is at 1 point, a secant's through 2. I know those are also trig words, so that's confusing, but we'll talk about that later. When we find slope through 2 points, it's really finding average rate of change. A slope is equivalent to a rate of change. Because it is, at its heart, we know back in the algebra days, change in y over change in x is slope. And it could be change in position over time. It could be lots of stuff. would you go to a point 5 units from point A? 1, 2, 3, 4, 5, which would mean A plus 5. Hard to say what that is numerically because I don't know what A is. So all I can do is call it A plus 5. Right? Now if I wanted to find the slope or the change between those points, or the slope of the secant line, I could do that. How could you find the slope, the secant slope, or the average rate of change between those 2 points? How do you find change or slope between 2 points? Let's actually go here. If I call this function f, then what are the x and y at this point? The x is, talk to me, a, and the y is f at a, whatever that might be. Okay? What about this point? What's the x? A plus 5, and the y value is f at a plus 5, whatever the function does to your input value. I don't know what it does. All right? Now, if I did the average rate of change, then it's change in y over change in x, or if you like, change in the f values over change in x. So what's the change in y? F at, let's use the second point, a plus 5 minus f at the first point, f at a, over change in x. A plus 5, a minus a. Wouldn't you agree that that simplifies to 5? Does that make sense that the change in x is 5? Well, yeah, right there, the change between from where I went, didn't I go a change of 5? The change equals 5. So the fact that this simplifies to be 5 is logical. You follow? So far, so good? Now my goal is to get change at A. So instead of going 5 away, I could do a little better by going 4 away. What if I started with A and went 1, 2, 3, 4 units? And drew the tangent, or the secant line. Sorry, the secant is through 2 points, and I'm drawing through 3 points, so that's the secant line. What's the average rate of change here? F at 4 plus A minus F at A over 4 plus A minus A, or 4. Wouldn't you agree again the change in x in this case was 4 units? Yep. All right. What if I got a little closer and took that second point only 3 away? 1, 2, 3 away would put me there. That's A plus 3 units. The point on the curve is there. Now my secant slope looks like that. What's the average rate of change, or the secant slope? F at A plus A minus F at A over 3. Change in y over change in x. The change in x, or delta x, was 3. Now we're getting closer and closer to the change in A. Now we could go 2 units away. Bless you. What's the slope? F at 2 plus A minus F at A over 2. 1 unit away is doggone close. Bless you. Here, F at 1 plus A minus F at A over A is the slope, or the average rate of change. All right. If we get closer and closer together, obviously we're starting to approach just touching at 1 point. Until those 2 points were so close together, they kind of melded together. I couldn't even tell the difference between those 2. Now, let's let this second point just be delta x away. A plus some little change, right? What's the slope now? F at A plus delta x minus F at A over delta x, or change in x. That's the average rate of change or slope between 2 points. Now, here's where the calculus comes in. They were able to get about that close in India, but without the idea, this fully fleshed out idea of limits, they weren't able to run it on for the touchdown. If we want then this to become closer and closer to the slope at a point, then what's happening to that delta x each time that I'm getting closer? Wouldn't you agree as I progress through here, I'm getting closer and closer to the slope at a point? Yes? Look at what's happening to the delta. 4, then 3, then 2, then, oops, this should not be A. What should this have been? Why didn't you say so, people? What is A or delta x approaching? 0. The change between the 2 points is getting smaller and smaller. So how would you say that? First of all, we said, let's find the slope between 2 points, A and some point a delta x away, minus the original point at A, over the change in x, which is delta, and we get them closer and closer together by taking delta x down to 0, and we do that with a limit. Now, I know your powers of memorization are strong, but I don't want you to memorize that. I want you to understand it. If you memorize it, it'll be there in a week, but it won't be there in 30 years when your kid asks you. If you truly understand it, it'll be there in 30 years. You'll get it, okay? All right. In essence, then, a derivative consists of two ideas. The slope between 2 points, which is that idea. And then getting the points closer and closer together, that's what the limit does. Taking the gap between the points down to nothing. Now, there are actually 3 different definitions of derivative, but all of them have that same idea. Slope between 2 points, get the points close together. Slope between 2 points, get the points close together. It's always that. It's just different notations or how it's achieved. Later, we'll talk this week, I think, about how it's achieved. Now then, if I want to use the definition of the derivative to find f prime at 2, now, first of all, right away, I forgot the order in which I'm supposed to teach things, and I probably needed to say, instead of this notation, which we haven't talked about, to find, actually, might as well talk about it now, to find f prime at 2. First of all, would you write this down? That's called f prime. That's how that's said, at 2. That's how that's spoken. And that prime is notation for the derivative. It's kind of Newton's notation. We'll talk more about the history of calculus. Newton actually, first of all, used a dot, not a tick mark. He didn't call it a derivative, he called it a reflection. Which I think is kind of cool. I wish that was stuff. At any rate, there are 2 creators of the calculus. In this case, we're using Newton's notation. So f prime at 2, and it means the derivative at 2. It means the instantaneous rate of change at 2. It means the tangent slope at x equal 2. It means all of it. A lot of verbal meanings to the derivative. All right. So I'm going to do this analytically first, and then we'll tie it back to the graph and say, what did we do again? All right. So let's just throw around the definition, just mindlessly throw it in the definition, and we'll tie it back to the graph. So let's start here. F prime at 2, maybe I should graph this one, is the idea of what happens as the gap between 2 points gets closer and closer together. Now, A here was just generally saying, you know, you want a derivative at some point A. In this case, they're not telling you some point A, they're telling you what point they want it at. They want the derivative or the slope at x equal 2. So it's not going to be f of a now, it's going to be f of 2. And so it's not f of a plus delta x, it's f of 2 plus delta x. That's the point a little away from 2. And then we talk about the original point was actually f at 2 over the change in x, which is x, right? You've done problems like this without the limit since Algebra 1. Saxon in his brilliance has given you the algebra skills to proceed since Algebra 1. And that makes your book special because most people are now also working through the function issues, not just the calculus. Let's make sure that those skills aren't too rusty here. I can go further because now in this case, in this problem, I didn't actually give you what the function actually is. In this case, now I'm telling you, for this problem, the function is x squared plus 1. So 2 plus delta x, doesn't that mean that in terms of using our function notation, if the function says square what you put in and add 1, then that's what I need to do. And then inside the function notation says what to put in. What do I put in? 2 plus delta x, all right? So remember the function says this is what you do, and the inside tells you this is what you put into what you do. So this is what I do. The function is 2 plus delta x, or x squared plus 1, and what I put in is 2 plus delta x. You follow? All right. That's just this so far I've done. That's f when I put 2 plus delta x. Now I need to also do another function calculation, blank squared plus 1. And when I come into this one, what do I put in? I put in 2. Now that's an actual number. I really do have a y value for that guy. And then the bottom, well, it doesn't, I don't put in anything. It's delta x. It's the small gap between the 2 points. All right? Now what should I do? Now, I'll just say this. If you try and do the limit right now, then if you direct substitute, you get 2 squared plus 1 minus 2 squared plus 1 over delta x. Now, really what's happening there is 0 over 0. Graphically speaking, you just tried to find change between a point and itself. You tried to find slope between 1 point instead of 2, and that's no change over no change. Every derivative will always, upon direct substitution, be 0 over 0 because you're trying to find slope at the points right next to each other. Can't do it. So we know that in calculus, if you want to do a limit and you get 0 over 0, you do more. You say, all right, well, maybe I can clean this up with some algebra. So what is 2 plus delta x? Squared. Sorry. 4 plus 2 delta x plus 2 delta x, so 4 plus 4 delta x plus delta x squared. I wouldn't take off if you didn't put that in parentheses, but it really is the whole thing squared. That's all one term, so it should be parentheses. Plus the 1, and then if we evaluate and distribute, what's 2 squared plus 1? 5. I think somebody said 5. I hope somebody said 5 over delta x. All right? How does that simplify? Look at the constants in the numerator. What happens to them? Okay, so the constants drop away, leaving me with 4 delta x plus delta x quantity squared over delta x. That's still 0 over 0, but what can I do? You can write out a delta x, which leaves you with 4 plus delta x. Now can you evaluate the limit? And what is the limit? 4. All right. Notice, first of all, in terms of writing, I talked about this on last night's homework, the limit stays. It stays, I didn't put 0 in yet. It stays, I didn't put 0 in yet. It stays, I didn't put 0 in yet. Stays, I didn't put 0 in yet. Only until I can actually put 0 in does the limit go away. Right? So the limit statement should be there all the way throughout until the very end. You with me? Let's look graphically at what we just did. What does x squared plus 1 look like graphically? Parabola shifted half. Up 1. So At 1, at 0, it would be 1. At 1, it would be 2. At 2, it would be, 5? Like that. When I found f prime at 2 equals 4, that means if I tried to draw a tangent line at x equal 2, the slope of the tangent line is 4. Or the rate at which it's changing at that microsecond is 4 units y for every 1 unit x. That's how fast Usain Bolt is going at that second. Are you down? Are you with me? Okay. Next idea. Now that represents the slope of the curve at x equal 2. If I then asked you for f prime at 3, that means what's the slope at 3? What would you have to do? You'd have to do all this again, but instead here, this would look as, this is good practice. The limit is delta x goes to 0 of f of 3 plus, as a starting point, minus f at 3 over delta x. And I would have to then do all that stuff, simplifying the algebra, cleaning it up, and finally getting a number. And I could, if they then said, all right, problem 2, find f prime at 4, then I would have to, then lots of work. If I wanted to find the slope at 4, which is probably way steeper, I would then have to set up a totally new average rate of change or difference quotient and do all that algebra to get a number. And then if they ask for f at negative 8, I have to do all that again. And that would really stink. Do you agree? Yes. Right? So rather than find every point and making all these little calculations for each end, instead we could say, forget this nonsense. We're going to, instead of doing this at 3 and 4, we're going to just do this at any old x. And when we do that, when we carry this out, x plus delta x, any old x plus a little point away, minus the original point x. This will give not a numerical slope, because obviously I'm not going to get the slope as 5 at every x. Instead, it'll be a rule for the slope based on whatever x you put in. Okay, so if x is, if you put in an x of 2, then boom, the slope would be, I put it into my rule and I could find a numerical slope. So this is not a, gives not a numerical slope, but a rule depending on what x you want the slope at. All right, so where? So am I in the right place? Is this the next place you know?
Yes.
Okay. So the objective now then is to find not the derivative numerically at one point, but to find a rule for finding the slope at all points, which is the derivative. Not the derivative at 2, just the derivative at all x. Start here. Notation-wise, you would say that. How do you read that again? F prime of x, or f prime at x. That's fine. F prime at x. We start by saying, now, just so it's clear graphically, we're talking about a point x and a point delta x away, finding the slope between them. So all the way from the very beginning, didn't we say, all right, find the change in y between the two over the change in x? That gets the slope between 2 points. What's the verbiage for that? Slope between 2 points? Secant slope. That gets the secant slope. And then we get the points closer together by using a limit. The limit takes the gap, which is delta x, down to 0, so the 2 points get closer together, and it approaches slope at 1 point. Now, let's go to problem specific. In this case, f is x squared plus 1. If f is x squared plus 1, then generally speaking, anytime I do a function, I say blank squared plus 1. And so in the first case, this guy will be found by taking something squared plus 1, and the inside tells me what to put in. And then the second guy will be also saying, well, the function is something squared plus 1, and the inside tells me what to put in. So what do I put in the first case? X plus delta x. And what do I put in the second case? Just a plain old x. Okay. In the bottom isn't really anything going into the function, it's just delta x. It doesn't do it. Please, I beg you, please ask questions and say, I don't understand where you're getting this. This, just that function part does trip some people up. And about 4 of you probably make some errors the first couple days on that, but that's fine. It happens. I know it happened to me. I was one of those 4. So we need to now evaluate the limit, but it's way too sloppy. So let's clean it up with some algebra. What's the square of x plus delta x? X squared plus 2x delta x plus delta x squared. The 1 is still there. And if I distribute the negative, it's so crucial that you have those parentheses or brackets there around the second thing, because that negative gets distributed to both the x squared and the 1. And if you don't use those parentheses, then your derivative will come out wrong. All right. With cleanup, what do I get in the numerator? Well, what happens? What goes away? What goes? The 1's go away. Check. What else? The x squareds go away, leaving you a 2x delta x plus delta x quantity squared over a delta x. What then could I do? What could I do next? I could hack a delta x, leaving me with 2x plus delta x. Now can I evaluate the limit? Yes, the limit is 2x. Now, again, remember the objective was to get a rule for the slope at any point. So it's good that there's an x there. It's not a number. Don't let that freak you out. That's great. It says then that, oops. Okay, sorry. This says if you want the slope at any point on this curve, just take double whatever the x is. So we tried 2, didn't we, earlier? If I put in a 2, what's the slope at x equal 2? 4. Is that what we got? Yeah, it's exactly what we got. What about the slope at x equal 1? 2. Does it make sense that that slope is not as steep as at 2? Yeah. What's the slope at 0? When I put 0 into the rule, the slope is, does that make sense? Yeah, you just found the minimum without a calculator. That's one of the uses of a derivative, is to find the extremum. What about when you put negative x's in? What kind of slopes will you get? Negative slopes. Does that make sense on this graph? Yeah, for any x, aren't those going to be negative tangent slopes? And as x gets bigger, what should happen to your slopes? They should get bigger. Does that make sense graphically? Yeah, the slopes will get bigger and bigger as x gets bigger. So it all makes sense. Now, that said, then, the derivative, I should have done a little better here. This was the slope not at all points, but at a point. And so this represents f prime at a. The derivative is specifically at some number. A might be 2 or 3. But what we just did is found a rule for the derivative at any x. And when you find a rule for the derivative at any x, instead of f of a plus delta x, it's generally f of whatever x plus delta x minus the original point. Okay? And this is a rule for the slope at any x. You follow? Okay. That said then, let's try this. Would you try to use the definition of the derivative to find the derivative of the square root of x at 2? See if you can figure out how to get started. Start by saying f prime at 2, or the derivative at 2 is this. Those of you who have seen calculus, you might say, do I have to use the definition? Can I use the power rule? The answer is 100% no. You cannot use the power. 100% yes, you must use the definition of the derivative. It will not just be wrong if on the homework you take shortcuts. It will be skipped. Use the definition of the derivative or else. Basically talk it over with your mathematics and say, does this sound right? This is super abstract. It's definitely ask-worthy. Check with a colleague before you go too far with your algebra to make sure you have it set up properly. Good job checking. Way to go. Question. For the first one, is your end goal a number because it's only one slope, or a rule because it's many slopes? Do you want, does this first question ask what's the slope at a specific point or any old point? A specific point. It should just be, how many slopes should there be at 2? Just one or lots of them? Just one. So what kind of answer should you get, a number or a rule? A number. It should be a numerical slope like the first problem as an example we did. So hopefully your first step looked like that, and the second step then is when the problem, it depends on what the problem is. In this case, it's square root of x, so f is this. It's not squared anymore, it's more like that guy, yeah? Did you get that second step successfully? Okay? Okay, if you try and direct substitute, what do you get? 0 over 0. That's a problem. So what should you do algebraically? We talked about this problem. What do? Multiply by the conjugate over itself. That gets rid of that problem. Sorry, normally I wanted you to do this all the way through, but this should be plus, yes. Otherwise, it's not difference of squares. Thank you. You're absolutely right. So, once you get 2 plus delta x minus 2 over a delta x and 2 plus delta x plus root 2. And I think you'll see that the delta x divides away. When it divides away, you have 1, and in the denominator you have square root of 2 plus delta x plus root 2. Can you put a 0 in now? Yeah, you get 1 over root 2 plus root 2. Suppose I could add those. What do you get when you add those? 1 over 2 root 2. That's the derivative at 2. All right. We didn't have time, but if you really are on your game, we could maybe, I know it says use the definition, but maybe we could kind of anticipate this. Do you agree 2x plus 1 is a line? So what's the rate of change at every point? Yeah. Now, when you have a curve, does the rate of change or tangent slope change? Yes. But when you have a line, does the slope change? No. And so what should the derivative come out to be? The rate of change for this problem, which in this case is 2. And although I'm technically finding a rule, isn't that derivative or slope going to be the same at every point, not depending on x really? So in the interest of time, that's where we would be headed here. You would see that f prime at any x is always 2. And you should be good to go on the homework. And I will be here after school or before school if the homework doesn't go well. Have a great day. It's so exciting for me. This is a really big step forward. And I will also say this: if you were just kind of thinking, I kind of get it, fine, I'll take it. Okay.